In the realm of physics, the discovery of new states of matter always sends ripples of excitement through the scientific community. Such a discovery occurred recently with the confirmation of time crystals. These enigmatic entities challenge our understanding of how matter behaves at the most fundamental level. Imagine a crystal, not frozen in space, but in time. A structure that repeats itself, not across physical dimensions, but through the fourth dimension, time. Time crystals defy conventional wisdom. They exhibit perpetual motion, not in the way a swinging pendulum does, but at the very core of their being. This perpetual motion, however, is not fueled by any external energy source. Instead, it arises from the intrinsic properties of the time crystal itself, a characteristic that seems paradoxical and almost magical. At the heart of a time crystal is a concept that seems counterintuitive: perpetual motion, without the need for energy input. To grasp this, we need to delve into the quantum realm, where the classical laws of physics often break down. Imagine a system of atoms cooled to absolute zero, the lowest possible temperature. At this temperature, all classical motion ceases. In this frigid environment, quantum effects dominate. Atoms, instead of being fixed points, become blurry clouds of probability. They exist in a superposition of states, occupying multiple positions simultaneously. Time crystals exploit this quantum weirdness. Their atoms are arranged in a specific pattern that repeats not in space, but in time. Imagine a ring of atoms, each spinning in a particular direction. In a time crystal, this ring of spinning atoms would flip its spin orientation at regular intervals, forever oscillating between these two states. This oscillation, however, requires no external energy. It's driven by the inherent quantum properties of the system, the consequence of the atoms' superposition and their interactions with each other. The very existence of time crystals seems to challenge some of the fundamental principles of physics. One such principle is time translation symmetry. This principle states that the laws of physics are constant over time. A physics experiment should yield the same results whether conducted today, tomorrow, or 1,000 years from now. Time crystals, however, break this symmetry. Their inherent periodicity, their oscillation between states, means that their properties change over time. This doesn't mean the laws of physics themselves are changing, but rather that time crystals exhibit a novel form of order, a temporal order that breaks time translation symmetry. This groundbreaking concept has profound implications for our understanding of the universe. Another fundamental principle seemingly challenged by time crystals is the second law of thermodynamics. This law states that entropy, a measure of disorder, always increases in a closed system. Time crystals, with their perpetual motion and unchanging structure, seem to defy this law. However, it's crucial to remember that time crystals are not closed systems. They interact with their surroundings, albeit in subtle ways. These interactions, while not providing energy to the time crystal, allow it to maintain its order over time, preventing a violation of the second law of thermodynamics. The theoretical framework for time crystals was first proposed in 2012 by physicist Frank Wilczek. However, it wasn't until 2016 that the first experimental evidence for these exotic entities emerged. Two independent research groups, one at the University of Maryland and the other at Harvard University, successfully created time crystals in their labs. Both experiments utilized a similar approach, albeit with different systems. The team at the University of Maryland used a chain of ytterbium ions, while the Harvard team employed nitrogen vacancy centers and diamonds. In both cases, the systems were cooled to near absolute zero and subjected to a precisely tuned combination of lasers and magnetic fields. The lasers served to flip the spins of the ions, or NV centers, while the magnetic fields provided the necessary interactions for the time crystal to form. The researchers observed that the systems exhibited periodic oscillations in their properties, a clear signature of a time crystal. These oscillations persisted even after the initial laser pulse, indicating that the system was not simply responding to external stimuli, but exhibiting its own intrinsic temporal order. While still in their early stages of development, time crystals hold immense potential for various fields. One of the most promising applications lies in the realm of quantum computing. Quantum computers, unlike their classical counterparts, utilize the principles of quantum mechanics to perform calculations. They rely on quantum bits, or qubits, which can exist in a superposition of states, allowing them to store and process information in a fundamentally different way. Time crystals, with their inherent stability and resistance to external perturbations, could serve as excellent candidates for qubits. Their periodic oscillations could be used to represent quantum information, while their robustness could lead to more reliable and less error-prone quantum computers. Beyond quantum computing, time crystals could also revolutionize our understanding of the universe. Their unique properties could provide insights into the behavior of matter under extreme conditions, such as those found in black holes or neutron stars. Furthermore, time crystals could shed light on the nature of time itself. Their ability to break time translation symmetry raises profound questions about the fundamental nature of this enigmatic dimension. By studying time crystals, we may gain a deeper understanding of the very fabric of reality. The discovery of time crystals has opened up a Pandora's box of scientific possibilities. These exotic entities, with their perpetual motion and defiance of conventional physics, challenge our understanding of the universe at the most fundamental level. While still in their infancy, time crystals offer a tantalizing glimpse into the potential of quantum mechanics and the strange, counterintuitive world it governs. The future of time crystals is brimming with potential. As our understanding of these enigmatic entities deepens, we can expect to see groundbreaking applications in fields ranging from quantum computing to cosmology. Time crystals, with their paradoxical behavior and mind-boggling implications, remind us that the universe is far stranger and more wondrous than we could have ever imagined.